Great. Yeah, I'll just take a moment to say thank you. I'm really excited to share some of the work that a few of us have done at GSOC and lately in sktime. And so I'll be going through this notebook that relates to the annotation module, which 3 months ago looked quite different to what it does now, since we've quite a few of us have contributed to this and focused on that area of sktime. So what is annotation? Broadly refers to a range of techniques from anomaly change point detection to segmentation. And these types of techniques can be used in a broad range of applications. So before we do anything, we need to generate some data. And this comes from a data generation module that was actually written in the last dev days. So what we can do here is specify segments of certain lengths and in a multivariate, with multivariate random variables and with means and covariances. So the first time series will generate here. If you'll notice, they have all the same covariances and they're really only changing means. So we're seeing a mean multivariate mean shifting. We'll call that Y1, Y2. This isn't the only way to represent data. If we look in what's called the data space, so if we take out the time component and just map Y0 against Y1, we get another look at the data. And I'm mentioning this now because a few techniques further on use the data space as kind of the starting point for these algorithms. So we consider, in some sense, time series that really look like this, and we look at distances between points in this data space. So we have a visual of that now. We'll generate another time series, but this time, instead of changing the means, we'll keep them fairly constant, and we'll change the covariance structure. So we have a highly independent, two highly independent variables. And then in the second phase, we'll have highly negatively correlated variables and then highly positively correlated variables. And we can see this here. It might not be immediately obvious if we just are given a time series like this, but in this phase here, we can see kind of the independence come through. And then about here, we see the negative correlation, and then it changes phase to more positively correlated. So I think there are two different time series with very interesting dynamics that we can then test some of our new algorithms on. So looking at this one in the data space is interesting, right? So we have this, if you think of points traversing this 45-degree angle line from the positively correlated phase, and then the 135-degree angle from the very negatively correlated phase, and the independents are the dots otherwise. So that's something I can keep in mind. I'll just stop here to make a note. I'm going to say the word dimension a lot, but we use that in different contexts. So we often refer to a two-dimensional array of size m by n to represent tabular data. But I'm sometimes referring to dimensionality of the data space, which would just be the number of columns. So m, 2 columns gives a two-dimensional data space. But also, I'll shortly talk about intrinsic dimensionality, which is something else I'll get to later. So separate. Okay, so now we have our data. Let's analyze it with some tools that we've developed in sktime, or developed and interfaced. Okay, so we want to understand the phases and changing nature of these complex systems. And the first way we'll do this is by what's called a hidden Markov model. And this allows us to account for these observed events and basically that have hidden events within the probabilistic model that cause the observed events. So this is done by fitting a sequence of hidden states to the sequence of observations and finding the most likely path given emission probabilities, the probability that a particular observation would be generated by a given hidden state, the transition probability, the probability of transitioning from one state to another, and the initial probabilities, what they start at. And so this was some of the work that Mirae did for the GSOC. Okay, so right now we support implementation for univariate time series. So if we take the mean shifting multivariate system and just look at one of those for now, and we run the hidden Markov model, we see within this model there's a dependence on whatever the mean parameters are fit to empirically. And I will also note that this is kind of a relatively small data set of about 100 points. So this model is kind of susceptible to whatever the mean values are in the training data, whatever they come out to be. And Mirae, I'm sure you have another interpretation as to why for 3 given phases or 3 different components, instead of getting kind of, I'd say segment 1 here, we kind of get segment 1, segment 2 is kind of fit as this entire segment, but segment 3 is quite obviously then separated from the rest. So I would say that performs pretty well considering it's a small amount of data. Let's have a look at what our other methods do. So the next method is called Hidalgo. And basically this refers to what's called intrinsic dimensionality of data. And really it's just some sort of topological feature that describes the complexity and connectedness of the data as it exists in the data space. And really we're looking at the distances between some particular point and its neighbors and using that to infer what kind of, well, the dimensionality of the manifold that these points exist on. So in the process of modeling this, we introduce some sort of parameter that assigns each data point to a manifold, and that's really what we're interested in finding out. What's the probability that this data point belongs to manifold 1 or manifold 2 or manifold 3, and what's the dimensionality of those manifolds? And once we have this assignment and we have the dimensionality of that, we can segment based on these values. And so this is what it looks like here. So these points at the bottom, if I didn't explain it too well before, they're just the labeling system for these segments. And so for this mean shifted data, we see that there's some sort of segment, so we call it segment 0, is somewhat being found here. It's a little choppy and changey in this middle area, which is understandable, being the middle of kind of these 2 mean values. And again, the last section was pretty easy to find by Hidalgo. It's okay, I would say. It oscillates, if you're wondering why it oscillates between 2 phases, because this particular algorithm is agnostic to the autocorrelation structure of the data. It just throws these time series data points into the space of data, looks at distances between them, and then assigns them some segment value. Okay, let's look instead at the the covariant structure shifted data. And we run this as well. And I think this is where we start to see the strength of an algorithm like Hidalgo. I will mention also that K, similar to the number of components above in the hidden Markov model, is a hyperparameter that kind of needs to be fit via a separate procedure, but it's an assumption based on how many manifolds there are. And then this is then assigned to, this data is assigned to one of two manifolds. And these points at the very bottom are when it had problems deciding which it was, and it couldn't assign one with a certainty of above 80%. So there's three categories, so to speak. And so I'm personally quite impressed by these results, because we see basically of two manifolds, we see a really strong phase come about when it's negatively correlated, and then a positively correlated area is quite clear in these results in the labeled data. And of course, the mix between the two we see here, it's a little bit confused, but I think these results are quite promising. It is a Bayesian method and there's a Gibbs sampler. So the downside of this is that it's quite slow. So for instance, this took 37 seconds to run, as opposed to a few seconds for more rapid methods on the data size of 150 or so. So yeah, you can always adjust the number of iterations to speed up the algorithm at the expense of accuracy. So moving on to, I think, our last anomaly detection algorithm. So this one's called STRAY, Search Trace Anomaly Outlier Estimator. And basically, again, it just looks at an improvement on a powerful algorithm that already exists, HD outliers, to better deal with non-stationary behavior. So how did that go with our mean shifted data? Well, we couldn't find any anomalies. So, well, I don't think there really are any in there anyway. So I think that still makes sense, these results, these null results. But I just said, suppose that maybe this data point and this data point chosen arbitrarily were exchanged. And what would that look like? Would that be detected? And it indeed was. I liked this because it wasn't too obvious an anomaly, but it was definitely a change to the generating system that was used. So that's promising data, and I would promising results, and I would be keen to see how this performed on a broad range of data sets. So but prior to this implementation, STRAY only existed in R, and yeah, so it's exciting to have this in sktime, I think. And so I'll just finish up now by saying, by explaining something else in regards to kind of building pipelines. So we have the data generation, the analysis tools, specifically for kind of segmentation, anomaly detection, change point. But there is also now a, in the case of higher dimensional data, there's now a dimensionality reduction tool that we can use that is specifically for outlier detection, and it's called Doben. So PCA is commonly used to reduce the dimensionality of data. And to illustrate this, I've just the same as above with these kind of piecewise normal multivariate function, generated 4 different phases with means given here, and these are independent time series. Yeah, you can see here. So it is kind of obvious that there's a bit of a change to the system here, but when we look at this in the space of the data, what we'll see is there are these 3 points at the end that are vastly different to the rest, but it's not immediately obvious when we look at it. It's only from particular angles, right? So we now have this interesting data set to work with, and suppose that we started with 100 rows or 1,000 rows, and you can imagine that it might be difficult to miss outliers in higher dimensional space. And so if we run PCA on this, a lot of people may or may not know PCA is finds a kind of rotation matrix or a new kind of basis vectors that maximize the variance of the data. And so we do that. And so we start with this 3-dimensional data set. And this is what it looks like if we map onto the first two principal components. And these 3 yellow dots are what we see were I'm going to say the outlier points that were generated at the very end of that time series. Yeah, so it's not immediately obvious, and we can see this makes sense because really the variance is maximized at an angle which kind of it's going to behave. Sorry about my dishwasher. At about this kind of angle here. But as I said before, we want a dimensionality reduction technique that maintains the outlierness of particular points. And so what this does, instead of maximizing the variance of the data, we look at the distance between the k nearest neighbors and seek to maximize the maximum distances of that set. And so these are the results of Dobin when we find our basis vectors and map them in a similar way to PCA, we maintain the outlierness, which is pretty cool. So we can use this as a pre-processing step to then apply these other techniques that I was explaining above. And for those interested, these are the references to the papers that were then implemented. And there's in each case an original code base as well, that for the most part were written in R, some C, some C++, a whole mix. And yeah, I think I'll wrap up there and ask if there are any questions.
Yeah, I have a question actually about the last plot that you showed.
Yeah.
So do you think able to compare PCA to Dobin in this case? So this is like a visual comparison.
Can we compare it? Yeah, they essentially at the heart of it are doing the same thing. It's just the objective of it. So it's the same in the sense that you're finding these orthogonal basis vectors that are a transformation of the data. And we can use a subset of them to effectively explain what we'd like to explain most of the data. And in the case of PCA, the information we'd like to retain is the variance of the data. But in the case of Dobin, the information we'd like to retain with fewer dimensions or basis vectors are the outlierness of points. Although, yeah, so it's not a anomaly detection mechanism. It's just a pre-processing step. So you're right.
Because in this case, the anomaly can always be detected even when doing dimensionality reduction. So this is the goal, no?
Can it always be? I think so. For instance, we don't really know. I might have had a misleading color coordination system. So I just wanted to link those to the points that we could see were kind of separated from the rest at a certain angle. But they aren't deemed as outliers or not. I just wanted to highlight them. So at this stage, we haven't identified outliers yet or anomalies. We're just saying, find us a rotation that'll give us the best chance of doing that with whatever technique you choose to then apply. So it could be stray that only maybe some of those points would be outliers because they only one of those points fall within a particular threshold of distance from the rest of the data.
Oh, okay. Thank you for the clarification. Yeah.
Thank you for the question.
I think Chris might have a quick question as well.
Yeah, hi there. Thank you very much for the extensive outline of the technique. So I've got two questions. So first of all, are there any sort of statistical tests associated with the annotations? So in terms of, is there any way to determine statistical significance of this particular window as being, as a certain group of time series being related to each other? And secondly, is there any connection between annotations to, say, chow tests for structural breaks? So in terms of the application of these annotations to, say, economic data, have you seen anything along those lines as well?
Okay, I'll start with question one. Hidalgo has a really nice paper. It was published in Nature about how they validated their method, right? And so to do this, to test the tools, you kind of use some known data generation function. And so they had some sort of 9-dimensional ball and kind of 3-dimensional swirls and kind of put this data set together and looked at how well Hidalgo assigned each of these data points that were kind of randomly mixed together to the original dimension of the data, so to speak.
Right, so they sort of ran a Monte Carlo simulation and sort of just compared, say, the KL divergence between the two distributions. I mean, how's that done? I'll read the paper to see how it's done exactly, but
yeah, but you're right in the sense that it does run an MCMC algorithm, but so it's a give sampler, and kind of a non-parametric version of it, as in you don't have to tune any parameters for it, but no KL divergence in this case. But it's funny you mentioned that because I do use that quite often in other Bayesian statistics methods. So the second question, I actually have no idea. I don't know. What was the, you said the econometric data that there was a chai test?
Yeah, so in econometrics, what we tend to do is we run a chow test, which essentially just, you can think of it as 2 linear regressions at 2 points. And we try to test for the statistical significance of whether there is a break in the trend. And what we do currently, it seems quite silly. We just sort of go along the window and just run multiple chow tests and try to identify if there's a structural break at a certain point. So if you can have something like an annotations where you have a vectorized process where you run it once against the whole time series, that could vastly sort of simplify and identify where you should be testing hypotheses. So essentially just minimizing the hypothesis space for testing for trend breaks. That's what I'm seeing here, at least. And so I'm wondering if there's sort of, that's why I asked about statistical significance of the first question, and the second question about whether there's a connection to tests for structural breaks, and if these two can come together. But it seems like with the MCMC distributional comparison test, that's slightly not quite, we'll have to dig deeper. I have to dig deeper. A lot of different ideas.
Yeah, I'll open the floor to anyone else if they have a nice answer to that. I can get back to you on the Bayesian side of it later.
Right. So mostly I've been working on deep learning for time series, and one of the main motivation for why I wanted to have more deep learning models within the time series dataset and to work on the time series dataset is because you see DL models kind of being adopted in each and every part of computational problems nowadays. I mean, one of the main examples are within the language part of it, or whether it be vision, and it has become a lot more easier to use them, as well as they have become a lot more powerful as well. And at least in a lot of computational problems nowadays, you don't see a solution which does not have DL. When it comes to time series particularly, it is still in the more of a nascent stage, in an early stage, where in the current I think M5, there were only a few DL models, pure DL models, which were being used, but I think, at least I predict, there will be more and more DL models as we go on. And maybe due to that, it is important to have more DL models within the time series space as well. And the main reason why DL models are becoming important is because and a good way to understand DL in general is because they can act as function approximators. And by what I mean is that whether it be a non-linear function or a linear function, what it does is that given an input, it can map exactly to where the function would map. And in a sense, it is an approximation, but as and when you have more data samples, and that is becoming more and more frequent nowadays, because now you have more data samples with respect to each and every problem, as your more methods and more analysis are becoming data centric. It becomes easier for a model to approximate to a function, and since DL are able to also do it in a non-linear scale, it is just a faster way and a better way. It is becoming a better way to get the results that you want in a more convenient manner. And as I said, applying these particular concepts of the advantages of DL to time series data will allow us to probably get better results and probably get better use cases for different people as well. So I think there are two main parts on what I have worked on, and first of them was the migration of sktime DL. And just a quick side note, sktime, I think at least before this summer, there used to be another module. There is still another module called sktime DL, and sktime DL was essentially a different module which kind of derived from sktime, but it had all the particular DL classifiers and regressors with respect to it. But the main issue was that it was not maintained in the same standard of sktime, and the code, essentially the whole user journey was a bit different than what you would have for sktime, and the documentations were not up to the sktime standards and so on. And that is the reason why the main task was to migrate all these DL estimators from sktime DL to sktime, so that it is easier for the users and easier for the people who are working on time series data to directly like pick and choose which DL model they want to apply as easily as they would pick and choose any statistical model they want to apply from sktime. So these particular what is essentially consisting in a DL estimator. So when I'm talking about a DL estimator here, of course, currently it means classifier and regressor, and I am working on forecaster as well, but that is another topic for now. So when you talk about DL estimator, there are two main things that you want to talk about. So there is a network and there is a estimator. So what a network is, the actual Keras or PyTorch or TensorFlow code. In sktime's case, it is the Keras code, but it is the actual Keras code of what is happening within the DL network. So whether it be a simple multi-layer perceptron, or you have a bunch of linear layers or a convolution layers and so on. That is what your network is. Now these networks are then abstracted over a estimator class or a classifier or a regressor class, so that for the users, it is as simple as, you know what, I just want to use a CNN classifier on my data. I just pick that up and I just write CNN.fit, it fits the data, and I write CNN.predict and it predicts the data. That is now possible now. And in a sense, it is also possible because there is a whole base classes and the whole flow which has been designed in such a way that if tomorrow I want to add a new particular estimator, say that I'm making a new DL classifier, say something like ABC, and I just want to add that. It is very simple to add it. I just need to create a particular network for it, and the abstraction process, since it is common for all particular DL networks, it has become so much easier to just make it available to more users. And essentially the whole pipeline, there is essentially a pipeline which is designed in a sense now for the users to add more networks, and for the for the creators to add more networks and for the users to just try and use all different classifiers if they want to. Of course, that is not recommended. You should probably know which classifier you want to use and which data set, but it is really as simple as just trying each and every one of them when they want to. And although the migration is still underway, there are sktime DL, but now the process of migration has become simple enough. There are like bunch of instructions which would probably help anyone if they want to either attempt migration or they want to add a new estimators or they want to add new networks. It has become so easy that I would honestly suggest that new contributors can try it out, and it is one of the good first issues that people can try their hand at. And this has been one of the main tasks that I've been working on throughout the summer, mainly because the whole workflow had to be converted from sktime DL to sktime, and it had to adhere to the existing standards of the statistical classifier, regressor, forecasters, which are there in sktime as of now. As of now, sktime, it is really simple to use, and it is an abstracted process where the user does not really need to know what is happening within a particular estimator, just that they need to know about the estimator and they can use it. And currently, you are able to use it like that, and that is something I'm very happy about. Another part, as I was talking about, your main estimators which we have been working on is classifiers, regressors, and forecasters. Forecasters is something which do not exist in sktime DL as of now, but that is something I have been working on adding as well. So the thing is, DL forecasters is a completely new particular estimator. It is not a part of migration per se, but it's a new estimator that I have been trying to add. And the main idea behind is that it has to follow the uh, the standards of your DL classifiers and regressors, as well as follow the coding standards and design patterns of statistical forecasters. And the main reason for that is essentially what I've been telling in the previous slide as well, that uh, an sktime user interface has to be simple enough so that people are able to pick and choose whatever they want to use. And previously in sktime DL, it was a bit of a problem, especially with respect to the documentation and coding standards, that it was a bit difficult to figure out what is happening where. And hence that is one of the main reasons why it is important that whenever we do add new forecasters, whenever we do add new estimators, and we are able to ensure that not only is it following a particular set standard for all DL estimators, but it also has to follow particular set standards for forecasters. Because if tomorrow I just want to try out, I want to basically benchmark a VECM forecaster, for example, or a VAR forecaster or an ARIMA forecaster against your one of these CNN forecaster or MLP forecaster, I should be able to do as easily as I would do if it was all statistical only. So in a sense, one of the main challenges itself has been to make the particular DL models adhere to these standards and these particular things. And so again, as I said, it's currently a work in progress, and I hope that it finishes soon. And just a small idea of about which particular forecasters are available now, not forecasters, which particular estimators are available now. There are a bunch of estimators which have, so this is one of the issues with respect to migration, and it kind of explains step by step of either how you can try to add how you can add new estimators to sktime, how you can add new DL estimators to sktime, or how you can create new DL networks to sktime, or how you can migrate from existing sktime DL networks to this current to the main sktime module. Another thing is there are a bunch of networks which have been defined for sktime DL which are being migrated, and you have new networks you can try out if you ever want to, which you have your CNN classifier, FCN classifier. CNTC is more or less done, as well as Celestine FCN. You have your MLP, you have your TAPNet, and you have a bunch of classifiers and regressors which can be migrated so easily and used, and it can just be used as pick and choose. And that is one of the main accomplishments, I think, within this summer. And yeah, so I'll just continue. Shit. Sorry. Yeah. So again, after that, I have worked on a few other contributions with respect to your deep learning, and So another things which I have been planning to do. Oh, wait a second, the presentation is a bit weird now. Yeah. So one of the other things that I've been trying to work on is trying to just change the base classes design. Again, the main idea here is whenever you are defining a base class, the idea of defining a base class is so that you reduce the redundancy between the child classes. And in this case, there is a redundancy currently which exists between your DL based classifier, DL based regressor, and DL based forecaster. And I have been trying to design a whole workflow of how to reduce these particular redundancies, and that is what I've been working on as well. And another part is trying to add more features to existing classifiers and regressors. So um, although your sktime DL are already existing, your CNN classifier, your LSTM classifier, and so on, it just I have tried to add more features and parameters so that the users are able to have more customization and have a better experience in general. So that again, the whole idea is pick and choose, so that they are able to do it in a more free manner. And the last part is just adding a save load functionality. This has been worked on by me, Sagar, and Franz together, and mostly by Sagar. But essentially, the idea here is that so when you're trying to save your normal model, or I would call it when you're trying to save your statistical model, it is generally not supported by Pickle, but so that you have a unified interface again, so that you don't have to worry about deep learning models in a different sense that, okay, now I'm using deep learning model. Okay, these are the different documentations compared to what are existing documentation within sktime. Do I have to go through that? You don't have to. And the whole idea is to add more features and uh, add more features to the DL estimators in such a way that you don't really have to worry about DL models as completely different thing. You can use just as if it were a statistical model. And this particular save load functionality also allows for that. And I think it was a short presentation compared to before, but yeah, those are my contributions in this summer. I would appreciate any questions or feedback.
I have a quick question actually, Shivansh. First off, good presentation. And I think it's always really exciting to hear about like where we're at with the deep learning models, because I think there's a lot of interest in the community in like using these type of models for time series analysis. I was just curious, could you comment a bit on the saving and loading? How easy would it be, or perhaps like in the future, to like say I wanted to use like a pre-trained head of a model, how easy would it be to just save and load like part of the network?
Okay, that is something very interesting, because that is something I am working on like right now, not during sktime, but in a different sense. So what it is kind of related to what you call as transfer learning, in a sense that not exactly transfer learning, but you have a particular model, you train it on a different thing, and you fine tune it on a different thing. And the whole idea is that this particular information you are learning is you are able to transfer it to different tasks as well. In the current implementation, honestly speaking, it should be working. I mean, maybe we might have to modify certain things so that there is a whole pipeline, but since you are able to just download the model, and once you have loaded the model, you can fit it again as a fine-tune step. And so it should be possible for doing that as well. Although I have not tried it out on sktime, but I think it should be possible.
Nice. All right. So as Katie talked about a little bit already, we now have some hidden Markov models in sktime. So this is one of the things I worked on this summer as part of my GSOC. And I kind of wanted to just go into a little bit more detail so that people are aware of this as a resource, and also build a little bit the intuition behind hidden Markov models if people aren't familiar with that. So a bit about me, I kind of introduced myself already. Outside of sktime, I'm working on a PhD in computational biology, and my particular interest is in annotation questions, because I think there's a lot of really interesting problems you can solve if you can do annotation well. And I'm also interested in sort of building pipelines and thinking about how we can build more complex pipelines. I'm not going to talk about that today, but that's kind of the areas of sktime that I'm most interested in. And a quick outline about this talk. I first wanted to give a quick introduction to annotation, just for people who may not be as familiar with that goal. I realize Katie kind of introduced it already, so I might go a little faster on that section. Build some intuition about what hidden Markov models are, discuss the HMM estimator implementations in sktime, so you can kind of decide like what might best help you with your problem. And then also I have some pending work in areas that I think would be good for a new contributor to jump in as well. All right, so quick introduction to annotation. I'm kind of going to build this around an example problem. So imagine that you're a consumer watchdog blogger, and what you're doing is you're counting the number of chips in a bag that comes out of your favorite chip factory. And you do this every week, and you kind of count how many chips are in your particular bag, and you have this data as a time series. So it might look something like this. So you might be able to look at this data and see that there are kind of 4 obvious sections that are jumping out. Here, maybe, we could say, maybe this is the normal baseline for number of chips per bag that we would expect to see. Here, there's like all of a sudden this high variability that we're observing in terms of number of chips per bag. And so, maybe we could say, tell some story about that being due to packing machine malfunctions or something similar. And here, the variability is still low, but the number of chips, the mean has shifted down. And so this might be something that would be like evidence of shrinkflation or something similar. So the benefits of a robust annotation module, is that you can begin to identify these shifts in the data generating function. And these can be, multidimensional shifts, shifts in variability, shifts in autocorrelation. And so these are all interesting things that we've all seen in time series data, but it's important to be able to robustly and repeatably identify these shifts. So it's an interesting problem in and of itself. But once you can do segmentation, sometimes that's the end goal, actually, is that you can segment your time series data and apply interesting labels to it. But you can also use it as a feature extractor. So say you want to highlight different regions that might be behaving differently for some reason. You can use it as a data cleaning tool if you find outliers like Katie talked about. And you can also identify regions where your assumptions might break down. So say you have a model that works fairly well for large swaths of the data that you're observing, but there also are going to be regions where those assumptions break down. And there might be interesting reasons for the shifts in the data generating function as well. So if you can identify the shifts, it allows you to do more like complex data analysis. All right, so moving on from annotation generally, I wanted to talk a little bit about what hidden Markov models are in particular. So when I was telling the story about this fake data, I kind of talked about 3 types of states that the system might be experiencing. We might be in our baseline state, we might be in a malfunctioning state, or we might be in our shrinkflation state. And a way that we can start to think about this a little bit more concretely and mathematically, if you could imagine that the probability distribution function over the number of chips that we expect to see, given each one of these hidden states, is going to look very different. So I realize chips is kind of a discrete variable, not continuous. So forgive me for the somewhat continuous representation. But this is kind of just to put into words, to put into a mathematical sort of representation what I was talking about before. If we're in our baseline, we maybe have a slightly tight distribution around a certain mean. When we're malfunctioning, all of a sudden that distribution has a much higher variation. And in our shrinkflation state, we're still a tight-ish distribution, but we've maybe shifted down our mean. The other thing to think about is how these states relate to one another. So for example, we might start out in our baseline distribution, but every week there's some probability that the packing machine malfunctions. So what's the probability in any given week that we go from the baseline to the malfunction state? Similarly, if we're in the baseline, there's some chance that maybe the higher ups or whatever decide that maybe we can get by with fewer chips, and so we end up in the shrinkflation state. And similarly, each of these states, once we're malfunctioning, what's the chance in a given week that we're going to be returning, notice that something's wrong with the machine, return to baseline, maybe someone calls out that we're now getting fewer chips, we return to the baseline, and these states can also have some probability, perhaps a very low probability, of going back and forth between each other. Last but not least, you have to take into account that you have some probability of staying in the state that you're currently in. So if I'm producing a baseline number of chips, what's the probability that next week I will continue producing a baseline number of chips? So this is just to give some intuition of what I mean when I say transition probabilities. So a hidden Markov model is really taking these two ideas, and as Katie said, also an initial probability. So you might start out with some probability of being in the baseline or broken or shrinkflation, and saying, what is, can I use this to find the most likely sequence of hidden states? So I would just like to say for a second, I'm actually just talking about one application of hidden Markov models. This is not the only way that they can be used, but it's the most common way that I think people learn about them and learn about how they're useful. So this kind of allows you to do is what you've essentially built is this large probability distribution over sequences of hidden states. So here, this might be a nice sequence that we would like to see, baseline, 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 malfunction, 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 etc. But we actually have, a way to evaluate how likely any one of these given sequences is, given the data, given the model that we feed in. And there's a lot of really nice algorithms for finding the most likely sequence once we have that distribution. So why HMMs? So, I kind of came up with a very simple toy model. There may be, and in fact, I'm sure are better ways to solve this particular labeling problem. Oftentimes simple solutions will work very well for these type of things. So I want to say it's not always the only solution to these type of problems. It's not always the best solution, but it is a worthwhile algorithm to be familiar with just because it's very robust theoretically and practically, because in part it's been around for a very long time. So people used HMMs in part of the moon landing. It has a lot of rules within biology, music analysis, any type of sequence analysis, people use HMMs. And I think part of that is because you have this nice framework of building the probability distribution over sequences, there's a lot of nice algorithms for finding the most likely estimation very quickly, and for thinking about these things in the language of mathematics, just because it's been around for a while. And I also think because it's been around for a while and it's been proven to be a useful tool, it's something that people are familiar with, and I thought it deserved a place in the sktime toolbox. So moving on, maybe I've convinced you HMMs are useful. How are you actually going to use it within sktime, within a pipeline on your data? Well, first off, and I recommend this for most use cases, is we can actually just use a wrapped estimator from a pre-existing package called HMMLearn. So the reason why this is good is it's a mature package. So they've actually outsourced a lot of the most expensive steps of fitting an estimator to C++. So it runs a lot faster than a pure Python implementation. And it's built on top of a lot of common distributions. So for a lot of applications, one of these might be what you need. So far, we have Gaussian HMM and Gaussian mixture model HMM. And I'm working with a current mentee, Keiichi Taki, to implement some more. But I would say, because this has been around for a while, this is a good place to start. And of particular interest, once you fit a model, you can also do the sampling option for each of these estimators, which I think is kind of useful if you want to generate some interesting synthetic data, just as an alternative. So what does that look like? Katie kind of talked about this a bit already, where you're just importing this from our HMM package, the HMMLearn subpackage, and fitting it is pretty straightforward, where you're able to give algorithm of interest. You can also just pass in the number of components, or you can also pass in more complex parameters. So as Katie alluded to, depending on how you initialize, so as I was talking about, how these things are related, you can tell the algorithm a bit about what you expect, the probability over chips given the baseline function to look like. You can also tell it a little bit about what you expect these transition probabilities to look like. And those are all things that help it perform better, but you might not always have access to that information. So that's something that's important to think about. Yes, you can build a complex mathematical, estimation of all these different states, but a lot of it, is going to depend on what you feed into it. And so, I think these tools make a lot of sense where you maybe do have some prior knowledge of what you're expecting to see, or a prior like annotated sequence that can help a lot. But you always have to be cautious with these things. And I really appreciated Chris's questions towards Katie about how to evaluate and measure the performance of these things robustly. But if the HMM Learn estimators don't work for you, I also wanted to draw your attention to sort of an experimental module about HMMs within sktime. So I've also implemented a lot of the sort of brown feed work for writing an HMM within sktime itself. And the main reason why you might want to use this is that I've written it so it can work with an arbitrary emission function. So this might be useful in the case where you might have an empirical distribution. You don't have one of those nice distributions that kind of a lot of HMM Learn has been built around, but it's still fully in Python. It's a lot slower than the other HMM options. I've done some stuff to speed it up, and I might try and pass some of the expensive steps off to C++ in the future, but it's not going to work as quickly with a very large data set as HMM Learn is. But I just kind of wanted to highlight the fact that it had this slightly different functionality. So what that looks like is now we can define these emission functions and pass those in as an additional parameter into the HMM. So here, this is just a very simple example where we're, kind of just creating two Gaussians, which obviously, you could do with just the Gaussian HMM. You don't need this to accomplish this goal. But this allows you to say, this is what I'm expecting to see from my emission distribution function, and then actually pass that in as a parameter. And so, there might be cases where you want this added flexibility. It kind of then performs exactly the same as the other HMM estimator, where you're able to fit and predict your labels. And I'm planning on expanding this some more. Obviously, there's some pros and cons to working with the pre-established and, like I say, recommended way of working with HMMs versus this experimental module. But it's also kind of nice that we have full control over what this estimator can look like. And so I'm definitely open to like other ideas and suggestions of how we can improve this more. So I mentioned I have some pending work items. Like I said, I've been working a bit with Keishi to wrap some more estimators from HMM Learn, but there are some other estimators that could be wrapped. So if this is of interest to you, jump in on that issue. Again, you can find that on the GitHub issues list. I'm also just interested in this question of kind of expanding the probabilistic modeling approach for annotation even more. So I know Lukas in the past has called out some interesting algorithms that would be nice to use in the annotation package. And I think that there's a couple of us who are working on this. So it's an interesting direction that, if you're interested, we would love more people to work on. And lastly, I think improving documentation, improving how we're talking about these things and sharing the results is always, an interesting question and useful for getting more people to use the tool and have it be useful. So yeah, as I said, Katie also obviously has this notebook ready together for this, but I think more broadly, this is definitely something I've been thinking about. So last but not least, I just want to thank Google Summer of Code, first and foremost, for kind of supporting me to join sktime this summer. It was a bit random for me in a way. I mostly do biology, but I really enjoyed it, and I wouldn't have joined without the support of Google Summer of Code. And the community has also just been very, informative, good feedback. I really have appreciated working with everyone. And a special thank you to my three mentors, so Franz, Lukas, and Guzal, who all gave me a lot of good advice that I didn't always take. I wish I had. But yeah, it was a very, very useful experience.
No, that's not true at all. Yeah. You did take the advice.
Well, not always. Anyway, I would love to take any questions at the moment, though. I realize this might have been a bit repetitive with Katie's presentation, so I'm sorry about that.
I just wanted to say it was a great presentation. I didn't think it was, well, I can't say I don't think it was repetitive at all, because I think you did such a good job and like explaining the intuition behind it.
Thanks, Katie. Well, all right. If there are no other questions,
I actually have a question.
Oh, yeah.
Locus, you first.
Thanks. Have you used any of this in a practical setting, or is it mostly theoretical for you?
So I've actually used it a bit in the context of analyzing this type of data that I use in the lab, actually. So I just played around with it. And again, I wouldn't necessarily say this is the best way of analyzing it, but I can do a quick screen share actually of what I'm talking about, if that would be of interest. So with we work a lot with bacteria, and in particular, we're interested in this question of what do transcripts. So transcripts are RNA, and in life, you go from DNA to RNA to protein. And one question we've always had is kind of what do the ends of these transcripts actually look like? And this is a little non-trivial to answer, simply because these ends can be processed. You have these things in bacteria.
Sorry, Mira, if you're sharing your screen, we don't see it.
Okay, I'm actually just pulling it up so I can.
Oh, sorry.
Yeah, so I'm just pulling up the plot at the moment, but I will share momentarily. I'm sorry. All right, let's see. This is on me for trying to talk and pull up the thing at the same time. All right. Okay, so now I can go ahead and share. All right, so this is an example of the type of data that we work with, where we're actually, these are all the 3' ends. So RNA has both a 3' and a 5' end. And here we're plotting, we developed a special library prep protocol to just look at the 3' ends. And essentially, we just want to be able to robustly call some of these 3' ends. And so oftentimes they look like this, and it's very easy to do it because there's just a sharp peak, and you don't really need like an HMM to call this. But sometimes we have like more complex nature of the 3' ends. So it might look a little bit more like this with some sort of rolling thing. Here, I would say this is still fairly easy to call with a z-score type threshold. But we also have some peaks where the sort of transcript area around the peak is very complex. And so one thing we kind of played around with, I realized this was not super useful, but sometimes they look like more complex just tapers off, and we don't actually have a really well-defined peak. But we still wanted to try and robustly call the ends of these transcripts. So I played around a bit with HMM for this, and I've had some success with it. And I would be interested in applying it to other problems as well, but this is kind of the extent to which I've used it. It's a good question, Love Kush.
Oh yeah, and I had another question. So yeah, Mira, really enjoyed the presentation, and learned a lot out of it. I will definitely try to test this with some things at work. So my question is, you mentioned that you'd like to use C++ for the more demanding parts of the algorithm. Have you thought about using Numba instead?
I have. I've actually tried it with Numba, and I did not see a large improvement in terms of speed with Numba alone. So I did a speed comparison between HMM-Learn and Numba, and I think part of it is because the nature of the Vertivi algorithm, which is what you're using to fit the HMM, is it's sort of a sequential algorithm. And so I don't know, I was sort of surprised, and I'm not a Numba expert, so I would be open to doing some more work on speeding it up. But yeah, I tried with Numba and it didn't really help as much as I was hoping it would. So that's why I've been kind of thinking that I might go down the C++ route. It's a good question though.
Yeah, thanks. I've also had trouble with getting Numba to work well, but I think it's because I don't know how to use it yet. But luckily we have people who know, so maybe we can help each other. Awesome,
Yeah.
nice.
Yeah, actually, Mirae, your point about sequential and number makes complete sense because I see number shine when you have code to be vectorized using a for loop. That's where number really gets its substantial gains, is for loops and having numpy code underneath. But if you're really just sort of throwing a ngit around pure numpy code that's a radiant matrix operations that's run sequentially, you won't see that vectorization. And numpy under the hood actually calls its C++ routines directly almost and directly compiled. So unlikely to see benefits. I wouldn't go down that route if HMM is in fact just a purely sequential algorithm.
Yeah.
And I would also not use number in any libraries because it's a JIT compiler and this adds a ton of problems later. But there's also another option with, I don't know if you know Python, which is ahead of time compilation, which works better with NumPy, but you get similar problems no matter what you do.
Actually, as a follow-up to that, like, wouldn't Cython be a solution to this problem?
Cython?
Yeah.
I have not heard of that. I've also not heard. Andreas, could you just repeat what you mentioned would be useful?
There's an alternative which is Python. I can just post a link in the chat maybe, because this is, instead of number, this is ahead of time compilation and it produces C++ code which is wrapped then. And the Cython is that you annotate your code in Python to generate C++ code. It's a similar approach, which is more mature, but Cython doesn't work that well with NumPy. That's why I think Cython also uses this Python to get a speed up on NumPy arrays.
Yeah, you're right. Cython is not very famous with NumPy, actually.
Yeah, this is one thing which this Python actually does very well. It can speed up NumPy code. It interacts well, but it has other issues. So it's always, for applications, these things are fine, but if you want to expose it as a library, Cython might be well enough because you have full control, but it's a lot of work again, and it's the question which you're faster optimizing your Python code with Cython or writing C++ from scratch. But for library, often writing the C++ code is, in my experience, the best option.
Yeah, because in Cython, like, you should use a language which is a mix between C++ and Python.
That's very interesting. And I would actually just like to comment, I think Franz also said this in the chat, but we've been talking about how we're using Numba in the package currently, because there are some estimators that do use Numba. You know, for obvious reasons, I do think there is a significant speed up in terms of the estimators when using Numba. But, you know, I think this is something we've been talking about as a community recently. And, you know, particularly Andreas and Ali, if you guys have like suggestions or thoughts on that, I think it would be, yeah, really interesting to continue the discussion. And I am particularly interested in checking out Python because I'd not heard of that before. And I think I'm just going to pull up what Franz says. Dependencies that are not estimator specific, you know, we've been talking about like what should be a soft dependency and what should be a hard dependency, because currently Numba is actually a hard dependency of sktime, which, you know, has some drawbacks, has some advantages. We've been talking about that as a community. So yeah, I just wanted to say, I think that the two of you should definitely contribute to that conversation because it sounds like you have some useful ideas. All right. Well, thank you guys. I really appreciated the questions.
Excellent. So sktime is a living and vibrant community of developers and contributors, and we very much welcome and support new contributors. So this Dev sprint is one of multiple dev sprints. We have yearly, we organize yearly. And this one is with the topic of documentation, but we have these kind of events regularly. So I'm going to explain how to get started and also how to stay involved with contributions to sktime. So we have a new contributor guide. If you have been on our issue trackers, on an issue tracker or on our main documentation page, you may have already seen it. So on the issue tracker, there is an issue which is getting started. It also links to the main documentation page. If you enter via the main documentation page, at the top, you have the Get Involved menu item, and under that, how to contribute. The link is here. Maybe someone can share the PDF version of these slides in the chat. Then you have all the links. So the main first item is say hello to the community. We have a Slack space where we collaborate, and there you can ask any questions that you might have, or you can also request help with getting set up or with making a pull request. And it is normal, it is completely normal to get stuck with one or the other thing if you're new to open source contributions. Do not be shy and ask for help, ask for questions whenever you need them. Today, during the developer sprint, we're also here. A number of core developers will be here after this main event and help get you started. Same tomorrow. And even outside developer sprints, you shouldn't need to wait for too long to receive a reply. So I would highly recommend say hello on Slack in the contributors channel. So currently the greet bot, I think, directs you to the general channel. But if you say hello in the contributor channel, that's where most of the core developers are also watching. We have a set of good first issues that we have curated. A number of them are in the documentation space, but more generally, if you want to get started, you can subset the issue tracker to the good first issues. Also, if you are not familiar yet with sktime, a good entry point is trying to run the user testing notebooks and see, okay, whether you can figure out how to do certain things with sktime based on the tutorials. More details on this are contained in the documentation linked. I also want to point out we have regular contributor activities. So on Fridays, we have community collaboration sessions. These are meant to get introduced to core developers. They are meant for new contributors. Again, that's a regular time slot where you can just show up on Discord and ask for help, for suggestions on how to get started. We also have regular stand-ups for the work streams that are currently running on sktime, and we have a mentoring program which usually runs over summer and winter periods. So we'll have mentoring activities also starting in the winter period after this developer sprint if you're interested in mentoring. So that means you have regular meeting with one or a few of the core developers. You can contribute on your own pace. So usually we expect something between half a day or multiple days per week. Again, it's at your own pace. So if you have, say, a few hours per week to spare, you might still be eligible for mentoring. The requirement is you've already made one pull request. But for that, you can get help using the community collaboration channel or in a developer sprint. Current work streams that are running, so documentation, forecasting, deep learning interfaces, benchmarking workflows, annotation, segmentation. Well, that's been one of the focus topics of the Google Summer of Code over the summer. We're going to relaunch it for the winter, and pipelines are also a topic. On how to contribute, you may or may not be familiar with GitHub Flow. So we're using GitHub Flow. That's a Git supported workflow for code collaboration on scale, which means you will locally on your computer make changes to the code. There is the main code base on sktime. And because there's dozens and hundreds of people who are at the same time working on the code base, there needs to be some way to reconcile the different changes. And we have adopted GitHub Flow. If you're familiar with Git Flow, it's the same as Git Flow, but without a developer branch, feature branches and bug fix branches only. If you're a new developer, the workflow is fork the repository, clone the repository, create a local feature branch in which you work. You need to ensure that you can run the tests locally. That's easier than it sounds, right? If you do it for the first time, there's always something that's not working in your developer IDE, so don't be shy again to ask for help. Don't panic if something doesn't work. And then make a pull request. On the pull request, you have discussions with the core developers to review and give feedback, make change requests, and finally you merge. For your first contribution, it's sometimes a bit fiddly. Again, don't be shy to ask for help. Don't be discouraged. Don't panic. We are here to help you, and you can always ask for help in contributors channels on Slack, in the in-person virtual meeting on Friday in the collaborator session. So the contributor documentation, so if you just read all of it, it might be a bit overwhelming. So we've selected some parts for you to get you started there. So it's a developer docs location, GitHub Flow. If you haven't seen it before, it's spelled out line by line with the commands you have to type. The CI/CD, so the tests that run on the pull requests are described here. And we are also using certain code formatting conventions. It might be helpful for you to set up pre-commit, and there's also a documentation page for that. The best way to learn all of this, by the way, is trying it out. So trying to get started, maybe with a very, very small contribution, where you know, okay, what to do in the code or what to do in the documentation, and just to ensure, just to use it to learn the contribution process, right? So you don't have to worry about the code or you don't have to worry about the complexity of documentation, because you intentionally pick something small and simple to get familiar with how the contribution process works. And you know, once you've done it once, then the second time will be a breeze. So let's get started. You can pick one of the first documentation issues. I think Mirae has already shared the link to an issue where good starter documentation issues are collected. There is the issue 3686, which Mirae has conveniently prepared for this documentation sprint. Of course, if you need to learn about sktime first, you can go through the sktime tutorials, and that's also best consumed by setting up your own clone. Of course, you can do it on Binder, but I think the learning effect is better if you clone the repository and run the notebooks locally, or so you need to set up your Python environment, you need to have a developer IDE running, you need to clone the repository, and then if you can run the notebooks locally, you can also already start playing around with the documentation or with the code. You can also think about writing a nice notebook for the notebook prize. As Mirae has said, we have a prize for notebooks for non-core developers. And most importantly, don't feel shy, ask for help if you need it. We're here to help you. Contributors channel, Discord on Friday, the event today, the documentation sprint, and have fun. So quick question, Mirae, where does the sprint take place on Discord?
So I think that the sprint, my plan was just for it to take place sort of asynchronously. However, if people would like to hop on the Discord right now and work together, I think that would be really great. I have to go into lab, so couldn't head that up myself, but if someone else is able to, that would be really great.
Any questions on the getting started? Anyone need help? So we can have a quick look at getting set up and cloning the repository if you want. And let me just, can you still see my screen?
Yeah.
Yeah, I can see the slides, Franz.
Okay. What I'm now going to show is okay, maybe let's have a show of hands. If I say clone the repository, run the notebook locally, things they need help with doing that.
Yeah, I do.
Mm-hmm.
Yeah, I think it could be useful, Franz, because we're also recording this, and I would be able to put the example up on the YouTube later. So I think
Sure. Okay. So what I'm going to show now then is the documentation page and walk you quickly through it. Give me 1 second to find the window. Okay. Browser isn't working. That's odd. Okay. So let's get quickly started. Can you see this?
Yeah.
got it.
All right, this is the main documentation page on Git and the GitHub flow. And the first thing you need to do is to create a fork of the sktime repository. All right, so you can do this here. Create a new fork. That will create a new fork in your account. So fork is it's a clone, it's a remote clone of the main sktime repository, but it sits in your account. And so at the start, it's a clone, but it doesn't automatically update itself. So you also need to make sure as development goes on main sktime, you update your fork. So that would mean pull from origin, pull fork origin, that's main sktime, and possibly merge. Then, okay, so let's suppose this is the fork. So this is not the fork. But your fork will look the same. So it will say forked from sktime. And so there's graphical user interface ways to clone. So if you have GitHub Desktop installed, you can click here, open with GitHub Desktop, and it will connect with the application and create a clone. Alternatively, you can do this via the HTTPS URL of the repository. So this is what you need in the console commands for Git. So you would git clone, so from your fork, right? From your fork, it would look like this. And so you also need to configure the remote upstream. That's the main repository, so that's the URL here. And so sync. Now, if you start developing a new feature, then you need to create a new feature branch. Commit your changes to it, so add and commit, and then push. Finally, create a pull request. again, that's described here. So these are all console commands. So what happens here now between 6 and 7, right? You write code and you develop your code locally and you test your code locally. So for that, you need you may have to run the test suite in the in your VS Code or PyCharm developer environment. Then you have created some Python files, you add them, or documentation files, you commit, push, and you open a pull request here. And the pull request then, so let me just open how a pull request looks like. So once you open a pull request, it will, so let's see, a pull request where people have commented a lot. Okay, that's not a good example because it doesn't have a lot of a description. Yeah, this is a book bug fix pull request. So if you open a pull request, pull requests, this is how it's described. At some point you will see this window, and here you need to describe what you are doing in the pull request. So I have added a documentation page for XYZ, or I've added the following piece of code, or I fixed a bug. Right, so here is a pull request by Beth where she fixes a bug. So she says, okay, I'm fixing this issue, which is a bug report, and this is the way I'm fixing it. Reviewer, please focus on, okay, is this mathematically correct? And then there is a discussion with the developers happening below that. And in the end, right, if all goes well, this gets merged, and then it becomes part of the sktime main branch, which is released with the next release. So this typically, there's discussion going back and forth. Change requests require you to make more changes. Then, right, you commit your changes, you push your changes. That automatically updates the pull request. Does that help getting started?
Yeah, actually, thank you. So give me a general point of view. So I will dig in more into the documentations.
Excellent. Any other questions?
One quick thing I was just going to say is if you are not familiar with GitHub at all, there's also the GitHub desktop application, which will take care of a lot of the making a pull request, pushing to the main line. And I think that, if you're not as comfortable with the command line, or if you're new to GitHub, I think that can sometimes be an easier starting point. So just recommend checking that out as well. If you find yourself getting a bit stymied with remembering all the GitHub command line interface stuff.
Yeah, and there's an introduction to GitHub course as well. So it's self-administered, it's free by GitHub. I've pasted the link in the chat. So that mainly focuses on, I think, using the GitHub web interface, commits and pull requests, how they work. It doesn't include forks, it doesn't include local work on code. So if you haven't seen GitHub at all, that's also a good starting point.
Thank you.
So yeah, a warm welcome from me as well. Again, I'm Arik Ermshaus from Berlin, Germany. I'm a PhD student at Humboldt University, and I mostly conduct my research there with Patrick Schäfer, who's also very active in your community. And I've also been committing some of my research in sktime last year. And yeah, today I want to talk about time series segmentation. This is my main research focus, the main things I work on. And so I think because your annotation community is also quite big, as we also heard from yesterday, I think it would be a great fit that I talk about this. And so let me start. I will start by basically motivating a little bit the use case of time series segmentation, because it isn't maybe the most researched field. It isn't the research community isn't so big compared to like anomaly detection or classification, but I think it's a very useful and very important thing to study. So first of all, we can note that especially in the last years, we've seen a big increase in sensor data. And this sensor data mainly comes from the digitalization of medicine and of industry, and also basically from our mobile devices. So we all have smartphones that measure acceleration, gyroscope, magnetometer data that basically tells us information about human activities and health. And the medical data, for example, ECG, tells us about heartbeats, or we have seismography data that can detect earthquakes or so. And so there's a lot of this data, and in its original form, this data is really, really large. So we don't talk about hundreds or thousands of data points, but more of like tens or hundreds of thousands of data points. And typically these sensor recordings then contain all of the interesting dynamics that we later want to study with time series analytics. So for example, when we want to do classification, we first have to find the segments that correspond to classes, and then we can later basically train and classify on this. Or when we want to do anomaly detection, we also typically want to find one homogeneous segment of the data in which we then localize anomalies. And to do all that, we first, of course, have to segment the time series from this long representation into smaller segments. And that's where time series segmentation basically comes in. And here I have two examples. Here I have an ECG recording that shows you multiple medical conditions, which then, of course, have different signals. And here on the right side, I have a seismography recording from a earthquake in Japan, where you see quite a big difference from basically nothing happening to the earthquake. And then if we were to ask a domain expert, he or she could probably also tell us what actually happens here in the earthquake, because it has different phases. So then if we want to formalize the main research problem of time series segmentation, it's something like this. We want to split the time series at increasing offsets into meaningful segments, which then form the segmentation. So if we have this time series here, which is gyroscope data from a smartphone, I think, that captures human activities, we actually want to find these points here where the one activity transitions into the other. And this then basically induces the segmentation. And in this definition, there's the word meaningful. So we want to find meaningful segments. And this now is then basically the whole, I would say, research effort to define certain notions of meaningful. And this then also, of course, really depends on the domain. So it may be a mean shift, it may be different variants, it may be different probabilities, it may be different similarities in the segments that actually define why this first segment is homogeneous and why it's meaningful compared to this other one. And also this gives us kind of like the predictive power to predict this one segment and tell it apart from the other segment. And then, as I already said, if we can solve this problem of time series segmentation, this gives us basically a possibility to solve a lot of more complex and very advanced problems with time series analytics, which is, I think, very nice. If we look into the, I'd say, last 10 to 15 years of research, we've seen, or we can see a lot of tools and benchmarks and surveys. I will not go into all of them in this talk, so I highlighted a few of them. These are also not, of course, all publications, but a selection of what I would consider very meaningful ones. And I will go over a few of them and talk about their basic concepts. And I will not only focus on algorithms, but also talk about benchmarks and mention one of the last surveys. So let's get right into it, into the algorithms. And I try to kind of like connect this to not only talk about the algorithms per se, but also talk about the implementations and maybe fill the bridge how this could be useful to integrate in sktime. So yeah, the first set of algorithms, also very old ones that I will talk about are optimization problems. So here's the main idea that we can frame the time series segmentation problem basically as a minimization problem where we want to minimize the sum cost of the selected segments. So how is this formalized? Well, we have a search procedure here that gives us potential segments. Then we have cost functions that are defined that measure the homogeneity of these segments, or also you could say the cost of the segments. And then we have further constraints that constrain how many change points or splits we want to find. And this then can be formalized mathematically and basically solved via a range of algorithms. So one of the first was probably dynamic programming, and then there have been optimizations and approximations to basically speed up this search. And here then also we find this measure of homogeneity here as a cost function. There are different formalizations of this. For example, mean shift, changes in variance. We can apply kernels. We can look at non-parametric statistics, and there are like a whole catalog of notions how to measure homogeneity with these kind of cost functions. And here on the right side, you have one example of such an algorithm. This is a binary segmentation, an old algorithm that has been kind of like optimized over the years with optimizations like wide binary segmentation. And the whole idea here of BinSeg is that you have this time series and you always split it into segments, and you then always calculate the cost for these two segments. You do this for every possible split here, and then you basically find the split that divides this time series best into the first and the second segment, and then you apply this recursively, so you end up with segmentation. There was a very, very maybe one of the first algorithms that is really, really fast if it's applied with a, let's say, not so complex cost function, and actually leads to good results, as we will see later on. And this entire catalog of principles is implemented in a very nice Python library, which is called Raptures. And there they have extendable and configurable interfaces with which you basically can combine all of these principles here to come up with a search procedure and a cost function, however you like, and a set of constraints to apply this sort of segmentation. So I think this is very useful, and there's a great survey. I noted it here, where you can look up all the details. And as I will later also note, I think it would be it would be great to maybe have this as a soft dependency in sktime, because it's very, very useful. If we then go on, there is a whole another set of approaches or techniques which are based on similarity search. And here especially, the idea is to measure the density of similar subsequences. So we can see time series segmentation also as a clustering problem where homogeneous segments contain mutually similar subsequences in close proximity. So if we go here to the example, we see that here in the first segment, we have a lot of subsequences that actually looks the same. And then we can basically find the point, and this is exactly this point where all of the similar subsequences are contained here on the left side, and none are contained, or very few are contained here on the right side. And this then, of course, can also be measured. And the first algorithm that did this, proposed by Gagabi et al., was FLOSS. And this algorithm basically builds this red curve here. This is called an arc curve, which then tells you how many of the nearest neighbor arcs from the subsequences in this segment reach over to the other side. And if these are only very few, then it means that most of these subsequences here have the nearest neighbor on the left side. And so we can find this point and then say that this must be the first change point. And this can then also be repeated to find a more refined segmentation. There have been approaches that extend this kind of method. Espresso is one notable one, which extends this approach with positional subsequence information. So the main problem here with this kind of approach is when this first segment comes up again later on. So if this would be repeated here, you would actually have nearest neighbor arcs that reach from the left side to the right side. And then this kind of method degrades. And you can counteract this by actually also considering where these subsequences are located in the time series and make it more likely that a subsequence here finds its nearest neighbor in this segment and not in a repeated one later on. And Espresso mainly formalized this with other proposals and efficiently did this, and it works. And to note also, Floss is also implemented in quite a nice library, which is called StumPy. And that's also implemented for two use cases. So once for offline segmentation and also for online time series segmentation, which is quite rare. And I think that Floss also would be a very nice extension to sktime, because it's one of the latest domain agnostic methods that performs quite well on recent benchmarks. Then the last algorithm I will talk about before I go on to talk about benchmarks is the clasp algorithm. This is the one Patrick and I proposed last year. Here, the main principle behind this algorithm is that time series classification can also be formalized as a self-supervised classification problem. Here, you basically want to find the labels for different segments, and the problem then becomes to actually find this label configuration so that the first segment is represented, for example, by label 0, and then the two other segments here are represented by label 1. And if you find this label configuration, you can train a binary classifier, time series classifier on subsequences from these segments, and then get a high classification performance. In order to do this, in order to find such a label configuration, you can do this in the following way. I show it here in the workflows class. The first step that you have to do is you apply windowing to a time series, and then you actually label different splits of the time series. So you start and say, okay, the first few subsequences I label with class 0, and the remaining one was class 1, and you do this iteratively, and then basically take more subsequences into the 0 class and fewer into the 1 class. And so you basically create binary classification problems, because now you have labeled subsequences with which you can actually train a time series classification algorithm. And when you do this, when you, for example, then compute the cross-validation of these problems here, the resulting score, the cross-validation score will tell you how good this hypothetical segmentation that you created actually was. And this then nicely correlates with the underlying time series segmentation that is concealed in the actual time series. So if you go here to this maximum, you have the classification score with the or the highest classification score that then nicely correlates with the point in the time series where the first segment changed into another one. And this will then basically compute as a profile. You see this here nicely, where these local maxima correspond with these activity changes here in this example. And this can then be computed. The highest global maximum can be extracted, and you can kind of like Binzek does it, do this recursively, and then calculate this profile again here for the first part and also for the second part, and then find the second and third and fourth change point. So this is the main idea here of the class algorithm. And we tested this on 2 benchmark data sets that I will talk about in a minute. And it reaches good accuracy and state-of-the-art performance compared with the other algorithms. And it is also part of sktime. So here I have a code example. We also have a notebook where you can find a more thorough example of how you can apply class to time series, and it's just a few lines of code, and then you can create such segmentations and get all the profiles and plot them and investigate them actually. And we are also currently trying to advance this algorithm. We have parameter learning strategies under review and also ensembling algorithms to increase the accuracy of class and to apply it to new scenarios. And we are also right now trying to apply it in an online setting so that you can actually apply it in real time, similar to FLOSS. Then I want to briefly talk about 3 segmentation benchmarks, because I think aside from the algorithmic standpoint, it's really, really important to have large and really high quality benchmarks to actually measure the progress of the time series segmentation community. This is very much the case for anomaly detection now, and also the case for time series classification for a way longer time. And I think that this is very, very useful. It's not so common yet for time series segmentation, but I would like to see this more so in the future. And one of the notable benchmarks was published by the University of California, Riverside, which is the time series semantic segmentation archive, and it contains 33 annotated medium-sized to large time series. So this means like a few thousand to a couple tens of thousands data points from various time series from the biological, mechanical, and industry domain. And these time series were mostly retrieved from publications and then annotated and pre-processed. And one maybe disadvantage of the benchmark is the time series only contain 2 to 3 unique segments. So you have rather long time series with only a few segments, but at least you have this benchmark, and the time series are really high quality. Then you have quite a different data set, which is the Turing change point data set, which was published by Burke and Williams in 2020. And this data set contains mostly small time series, so basically just a few data points to a few hundred data points. And it also comes from various domains and captures financial data, climate data. Here we have passenger data and the examples. So also a wide range of domains, and quite interesting here, the authors actually made the effort to have 8 experts annotate this data with segments, and then actually also define evaluation metrics, how you can test your algorithm predictions with multiple ground truth annotations, which is really, really nicely done. And I also recommend to you reading their experimental evaluation, which is also very, very nice. And then the last benchmark I will talk about is the one that Patrick and I published with our paper, with the class paper. This is the time series segmentation benchmark. This is notably a semi-synthetic benchmark that was derived from the UEA and UCA time series classification archive maintained by Tony and his group. And here we basically took time series and grouped them by class label, and then concatenated them, applied some pre-processing, some resampling to create a semi-synthetic segmentation problem. And this then nicely, of course, includes all the temporal patterns and different statistical properties of the wide range of data sets that are available in the archive, and makes this available as a segmentation problem. And we took the effort to construct a quite diverse benchmark with 2 to 7 unique segments. More kind of like variation compared to the first benchmark I talked about. And we've also a lot of different configurations with smaller time series, just a few hundred data points, to very large time series with tens of thousands data points. And right now we also have one extension to the benchmark under review, which also includes time series with only 1 segment. So there is no change at all, which is kind of like the true negative case for time series segmentation. And then also with repeating segments, which I talked about earlier, where segments repeat, which makes the segmentation problem a lot more harder. And on this data set and the one from UCR Riverside, you see the clasp, but also BinSeg and FLOSS perform quite well. I also, to note this, we also have an open sktime pull request that wants to basically connect this GitHub where the benchmark is available to sktime as well, to make this available. As my last slide, I have the future directions for time series segmentation. So there has been a lot of research in the kind of like in the batch setting, where you have all the time series available, and you then conduct the segmentation, which is of course very handy from a research perspective. But I think it would also be very interesting to look at online stream segmentation, especially as most of the interesting large sensor data is actually recorded somewhere in real time on the device. And in some domains, it would greatly benefit them to get an early segmentation or an in-time segmentation, where the system actually tells you that some kind of change happened in the system. Then also, if you look into the literature, there are a lot of publications that are quite specific. They try to devise cost functions for very specific signals, but you only see very few algorithms that claim to be domain agnostic, or at least try to cover a wide range of signals, which I think is maybe where future research should look into more. And as the last point, also a lot of research is just focused on the cost functions, but I would say that it's also very interesting, and it needs more research to also look into the actual search of hypothetical segments and into the extraction procedure. So how many change points are actually present in the data? And as my last point for this talk, I think it would be very beneficial if sktime as a software library maybe could connect some of the last approaches that have been published, maybe as a soft dependency, or maybe also implement them directly, so that basically other researchers could use this in their publications, and it would make benchmarking very easier. And also it would be also very handy to just have these methods available and to use them for specific projects. And maybe as the last point here, it would also be nice to have data loaders or to have evaluation metrics for time series segmentation, sktime. And yeah, I think these are my thoughts for the future. So if you have any questions, shoot me an email, or maybe now in the Q&A. And thanks for listening.
Thank you, Arik, for this presentation. I have some questions. If you want, I can start.
Yeah, sure.
So about the benchmark, that the slide about the benchmark. Yeah, this one. So the data sets that are chosen for the benchmark are taken from the UCR archive. But not all of them. But the choices that have been made are given on what?
So we have excluded time series data sets that are really, really large. because we didn't want to have time series with like millions or few millions of data points. And we've made all the design choices, which data sets we actually chose and what kind of pre-processing we conducted. We've all made this public. So you can basically recreate the entire benchmark from the original data sets. And we also made the methods available to conduct the transformation. So you can also create your own ones if you want, if you like to. But for this specific benchmark, we've made some choices to get diverse problem settings.
Oh, okay. And my second question is, do you think segmentation on, for example, on the ECR archive, so on these data sets, can help in the problem of alignment of time series?
What do you specifically mean with alignment of time series? So finding similar time series?
Yeah. So the similarity metrics between time series, there's algorithms like that finds the best alignment between both. Do you think this can be used in order to like only align, for example, the segments instead of all the time series at the same time?
Yeah, sure. I mean, yeah. If you actually look into the last two approaches here, so one second. Here, so the clasp approach and also the plot approach, they mainly do this. They cluster time series from or let's say subsequences from the segments, and they give you they give you the points where the subsequences actually where they are mostly contained. And so this could maybe be interesting from an alignment perspective, but I think these are very, very different problems still.
Yeah, you're right. Yeah, thank you.
Yeah.
So I think out of interest of giving Chris enough time to have his talk as well, we might move on to him. But I just wanted to say, Arik, like I really enjoyed your talk, and you actually talked about a lot of stuff we've been talking about in the annotation work stream. So I know there's someone was working on a PR for Floss. I actually was planning on implementing Espresso. I haven't really made much progress on that yet, but and you know, we've talked about implementing ruptures. So I just wanted to say, like, it would be great to have, like, let me know if you want to be more looped in with the work stream, because it sounds like we're interested in doing a lot of the same stuff.
Yeah, sure. Yeah, we can stay in contact. That would be nice.
Yeah, and also just
I'll only add that there is also some metrics implemented for segmentation specific problems in sktime. So feel free to add more if you have some lying around.
Cool. Yeah, sure.
Okay. So first of all, let's begin with a story. A story of a data scientist, a forecaster in the trenches, working at some company, a reasonable scale company, a company that's not FANG scale, but a company that deals with perhaps maybe a range of 10,000 or even up to 5,000 products, and with daily data or even weekly data up to the last 4 to 5 years. So they start with, they've got the manager comes in, tells you, hey, I need a forecast. Can you forecast our sales for us for the next 2 quarters? So great, you pop up your Jupyter notebook, you get your autorema, you fit it on your time series, and boom, you get your result. Your manager says, that's great, that's fantastic. This line is good fit, that's fantastic. Now, can you help replicate this across all regions, customers, and products? And so now you have to start running autorema across all your different products, regions, or customers. In that case, that's still fine. Your autorema is relatively fast. You pop in the for loop, you go grab some tea, you come back, and it's done. So we're still good here. But of course, as we know, there's the no free lunch theorem, right? Different models tend to work for different data sets. And this often means that it's not good to just fit one model like autorema or ETS. You want to fit a whole range of different models because the likelihood is your data set will likely work best with a different model. And this is particularly true in the time series space, right? And a few things I want you to note is, first of all, Auto-ARIMA, the fit time, as we see now, is quite diverse. It can range from 3 seconds all the way to 60 seconds. If you ever wondered why this might be the case, well, is to remember to know that Auto-ARIMA actually tests in a stepwise function around 64 different models, right? But there is early stopping in Auto-ARIMA. So for instance, if your time series is relatively well behaved, right, doesn't have a lot of seasonality, is a simple single difference, maybe has a P and Q order of 1 or 2, the stepwise search early stops quite quickly. And that's why you get this extreme range in Auto-ARIMA training times, in particular for higher orders, and more on this later, right? And another point is also for ETS is that these scores is generally for things with seasonal periods less than 12. If you want to use ETS on higher order seasonal periods, the parameter space tends to explode, and the fit time can also increase exponentially. So there you go. Yeah, and really focus on the node-free lunch theorem, right? Because you see here, this is from the forecasting data archive from the Monash University. They benchmarked different models across different data sets, and you see that there is no one clear winner, right? There's no sort of go-to model that tends to work universally across all different data sets and all different domains. And so, you know, the complexity starts to explode now. You have to fit about 6 or 7 models across all, say, 5,000 products that you have. Okay, fine, but it's still manageable. You know, you just leave your laptop overnight, come back and see what it does later. But of course, later on, your manager comes back to you and says, hey, you know, these charts that you're giving me, right? It just looks like a bunch of squiggly lines. You know, it's like you got one product here, a bunch of squiggly lines, another product, a bunch of squiggly lines. And this is a real story. I've had a business manager, business executive say, tell me, what are these squiggly lines on the screen? And I said, okay, what's wrong with these squiggly lines? And he said, well, this is unrealistic. We can't have this, right? We are a supply chain company. I've noticed here that in some parts, your squiggly line is underneath the actual sales in the past. I see for some parts is above. Well, we cannot have it under, because if we ever fail to provide our critical, perhaps as a chemicals company, our chemicals to the specific company, we'll lose the client forever, right? Perhaps it's an operation that needs those chemicals immediately, and every second of shutdown for their machinery costs the company millions of dollars. So we cannot have, you know, the squiggly line ever go under actual sales. And say, okay, that's all right, that's fine. You know, I know this thing about, you know, prediction intervals, right? That's absolutely fine. And here I've got a picture of this is your manager, by the way, who is Nassim Taleb, telling you, hey, so yeah, you generate this parametric prediction intervals, and that's fine. But turns out your manager is, you know, Nassim Taleb. And he goes to you and says, no, this is not right. This is completely unrealistic, right? I've never seen this in my entire life. A symmetric distribution, how can something rise with the same likelihood as something decreasing? That's just unlikely. I mean, in some places, it might even decrease below the 0 point. And you start panicking, and think, okay, right. A kind of symmetric prediction intervals, what do I do? And then you remember back in your 3rd year statistics class in undergrad, oh, that's right. There's this thing called bootstrap, right? Bootstrap. You can use bootstrap confidence intervals to create a non-parametric prediction interval. And these non-parametric intervals are not dependent on your distribution assumptions. For instance, the normality assumption, which is generally symmetric, in which case, you know, your manager, they seem to come back to you and says, this is great, right? The reality is not symmetric. Things tend to increase or decrease in a unevenly distributed way. So that's great. But let's go back to your laptop, right? You're running all this in your laptop. You've got your 5,000 products. you've got this great variance in your models that you fit between 3 seconds to 6 seconds. You're going to fit around 6 to 7 models. And now you're running Bootstrap on top of them. Right, and this is particularly critical because, like I said, symmetric intervals are just generally unrealistic, particularly when you're trying to very accurately target certain quantiles. Right, a point prediction is simply will not run in an industrial workplace because having bias, even the slight bias above or below the actual realized value could cost irreparable damage. For instance, in DoorDash, they're always trying to target above actual delivery times because they know that if they do not deliver their orders on time, that will cause extreme damage to their clientele, and they might very easily switch to a different application. So here, right, having non-symmetric, non-parametric confidence prediction intervals are incredibly critical. But at the moment, the only really robust way to get these are for Bootstrap. But Bootstrap is extremely expensive to do. And of course, let's not forget, how are you going to evaluate these forecasts? You have to backtest. And usually when you backtest, and in my experience in industry, it really depends on your business executive, right? Some executives, well, most executives won't know that perhaps 5 to even 3 splits are oftentimes good enough for what you're trying to evaluate. But of course, they might want backtests up to the last 4 years ago, gives them the confidence, ease of mind, in which case you're going to multiply that, another multiplier back to that equation that you saw, the complexity of running forecasting at reasonable scale. And don't forget, this is already a reasonable scale company. We're not talking about a company with entire 100-team data scientists. It's just you trying to run forecasts for your reasonable scale company that does supply chain logistics at, say, 1 or 2 cities. So now you're thinking, okay, perhaps I need to start expanding away from my laptop. Right, maybe I can start using the cloud. But before we go into the cloud, let's just look at some numbers. So what you see here on the left is also part of the forecastingdata.com archive from Monash University. And essentially they've tested the compute times. They've measured the compute times for these benchmark models across a bunch of data sets. And you can see here, right, that the times are incredibly expensive. Right, for ARIMA, it takes 48 hours on a relatively large-sized computer. I don't know who here has a laptop with 65 gigabyte RAM, but I certainly don't. Yes, even with this sized instance, which is relatively large, not the largest instance out there, but relatively large, it still takes up to 48 compute hours. And let's not forget, these numbers are only for a single train test split, right? It does not include Bootstrap. It does not include backtest and evaluate with multiple windows into the past. If you add those up, that's a multiplier of B times Bootstraps, and the time complexity just explodes. And another important thing you have to remember as well is the RAM memory usage, right? Especially when using something like Pandas data frames, which, if you may or may not know, generates copies of itself for pretty much every transformation you run on it. And this is and time series forecasting is particularly expensive, hidden in a hidden way compared to, say, classification or regression. Why? Because of the recursive structure of many forecasting tasks, like rolling features, like shifts and lags. And what happens, especially in something like Pandas, which is eagerly executed, is that each lag you do, each window operation you make, it generates a new copy, and a new copy, and a new copy, and a new copy. And when you run this across all your n time series, and you run it across, and each and every one of them is associated with its own ARIMA model, you're running these recursive copies over and over and over again, and these very quickly accumulate. And from our own internal tests in my company, we found that we need an instance of about 18 to even 150 times larger than the size of our single data frame. Yeah. So this back to the question, can we use the cloud? You heard about this new fancy thing. Well, not new fancy, it's been a while. Around for a while, you got Spark, you got Git, you got operation. Because as you know, right, this is an extremely parallel operation. You can split it across time series, you can split it across models, and you just run on the cloud in the distributed compute system. And as you can see here, this is taken from a recent PR that we have in sktime as well for a parallelized backtest. And you can see here, you have this is an extremely efficiently made implementation of backtesting already. If you look on the bottom left corner, these are the number of tasks that the individual workers are processing. So you're pretty much every worker is working its full horse with the current implementation. And on top of that, you see that the bar, so each bar you see on the screen represents a task in the distributed compute engine. And you can see they're all relatively close together, which means you've got tasks coming one after the next, after the next, and the next. So in many ways, this is almost a fully optimized implementation. But even in this case, right, I want you to pay attention to the white spots in between each green task. You can see that these white spots still exist. And what are those white spots? Those white spots are your communication costs. The costs of transferring data, the cost of serializing and deserializing data. So it's very important to remember, even if your problem is, oh yeah, I'll finish off the conclusion for that, but essentially, right, beware of these hidden costs when you're trying to distribute, right? The cloud may not be your savior. Distributed compute may not be your savior. So there's this blog post recently on Mirae with StatsForce where they claimed you can spend less than $30 in AWS to fit 1 million time series. But it's very important to remember that almost, I think pretty much every single blog post I've seen so far, it is vastly underestimated, right? Because these only include the instance cost. It only includes the hourly cost of running that server. But what we've found is that it is only a fraction. And in fact, not even a majority fraction of the costs. There's a massive cost, hidden cost that AWS does not tell you, related to transferring information between workers. So between different instances that you're running in this distributed compute system. Between your storage, whether it's S3, so your S3 object storage to load your time series data into the distributed compute to run the training routine, or loading it from a database, right? Every single transfer costs money. Every single serialization and deserialization operation in this entire system, and don't forget, every single task has to be serialized and deserialized across the distributed system. That also costs money. And so all I'm saying is, cloud to the rescue, maybe, if you have the money, right? And this is why, you know, we're probably all going to end up funding Jeff Bezos' second trip to space. But it's really important to remember that right now, as of this moment, companies that claim to have serverless distributed compute is oftentimes still magic, right? So, for example, Databricks, which is the managed version of Spark, has this thing called ephemeral clusters, where you can sort of spin them up and you can destroy them directly from your laptop through 2 commands. Yes, that is possible. Yes, you can do this in something like Dask and Coiled as well, but oftentimes that's not the cost that accumulates the most. It's the networking cost that accumulates. It's the communication cost that accumulates. It's also the cost of testing the system, right? It'll be in the perfect world, we write some code, we send it to our distribute system, it runs without bugs, and you get your result back directly in memory to your Jupyter notebook. That would be a perfect world, but that does not exist. And these costs slowly accumulate. And the heuristic that my team has developed when you're working with these kind of distributed compute systems is take your instance cost, multiply it by how long you think your training routine would be just for the instance cost, and then multiply it by at least 5 to 6 times. And that would be perhaps somewhere closer to what you really will be taking on. And this is not, and this is completely negating the complexity of what you're trying to run. If your distributed routine is a lot more complex, for instance, something like GBM, right? Like GBM has the distributed version of it on Dask has many very interesting statistical operations underneath to parallelize the trees in Dask. Lots of very nitty-gritty, low-level custom code. I'm sure that the cost to test that system also accumulates, and the time to test that also accumulates. So yeah, beware of hidden costs. These quickly accumulate, even if your problem is embarrassingly parallel. And of course, let's not forget, when you're running all these benchmarking models, these univariate models at scale, like you're fitting 1 REMA per time series, you must also add in the inference cost, right? And generally speaking, the inference cost is constant across different models, unlike the fit time. But it is still a significant, it's a non-negligible time and space multiplier, right? It's a time multiplier because you still have to run it across every single time series and across every single model. But it's also, I think, more significantly, and this is something people generally forget to factor into their costs, it's a space multiplier, right? Your predictions have to be serialized and deserialized. Your predictions have to be stored somewhere afterwards, especially if you're trying to run a system in production for all your different products, right? You don't want to be collecting your results back in memory. That would be a terrible thing to do. If you were collecting results back in memory in a Jupyter notebook and something went wrong, you would lose all the intermediary results that you're saving. So what this means in practice is just like how you're loading in your data from S3 or loading it in from your database. After you run predict in this distributed system, you should also be storing it again in your object store like S3 or storing it again directly in your database. So you don't lose the successful intermediary tasks, right? But of course, IO, input output, is the cost is non-negligible. It takes time. And that also accumulates to your instance cost, to your distributed compute cost, like I mentioned beforehand. So what's the solution, right? What's the solution? Well, in the last about 2-3 years, there's been more direction both in research and industry, both in academia and industry, towards something called global models. And the global models is really quite, in my mind, it sounds fancy. It sounds fancy, but in reality, something quite simple. And then feel free to jump in if you want to disagree with me. In my mind, it is really just, you can think of it as a panel model, right? A panel being the classic data set where you've got a time index and you've got an entity index. For instance, you want to run a simple regression of, say, countries' GDP over time. That's a panel model. Actually, I'm sure everybody here knows this already. So I probably don't have to go into too much detail about that. But essentially, a global model is just a stacked panel model. You've got your time and your entity, and you stack on top of each other. And what you do is you run your forecast model across all of these points at the same time, right? So what's the benefit of global model in the context of industry and production? Well, first of all, it's significantly faster fit, and I'll show you some numbers right after this slide. But I think more importantly, right, you get bang for buck RAM and CPU usage. I think this is really the critical idea, is when you're trying to scale univariate models across your product line, time series, whatever simple scale company you're working at, there's a lot of hidden costs. cost of serialization, your serialization cost of I/O between time series, cost of even spinning up a distributed compute system on your cloud. Lots of hidden costs. Sorry, my internet is unstable. Hello. Okay, seems to be back. All right. But if you have a global model, you fit your entire data set in memory, and you run your model entirely from that memory stored, that in-memory representation of your data set. Right. I mean, this is the revolution that you saw in deep learning and for NLP and computer vision. Right. They have massive models, single models, trained on single servers, vertically scaled. Right. And the reason why the cost benefit makes sense in those cases is because communication from memory to your single instance is a lot cheaper. I mean, significantly, it's unthinkably cheaper than what you see in the distributed system where you have to communicate between workers, communicate between processes, or even communicate between servers. Right. And lastly, you get the inference speed up. So you remember previously in the equation where you have to have n multiplied by the n multiplied by the fit, by the predict times, where you don't have that, right? Because if you have a global model, you can have a vectorized predict, where you just run predict once across all different time series on a single instant in a single process. And here are some numbers. Once again, also from the forecasting archive from the Monash, from Monash. You can see here that the global models, which are highlighted in green and purple, are significantly faster than the benchmark models of ETS and the RIMA, right? Up to between 2 to even 20 times faster. So the question is, do these models work? It seems so. In a working paper from Hindman and Pablo and Manso in 2021, they found that autoregressive ML global models, so essentially just a simple regression with an AR structure, but in a panel format, seems to have the same performance, or seems to converge towards the performance of the classic many different multiple ARIMA models, singular ARIMA models, as long as they're long enough memory. So the chart that you see on the right-hand side, the dark black line is the global models performance. The dotted line you see is theta ETS ARIMA, and the x-axis is a MACE score, so mean absolute scaled error. So x-axis is the number of lags, and the y-axis is the mean absolute scaled error. Sorry, my bad. So what you see here is as you go further down the x-axis, so the number of lags in the global AR model, it seems to converge in the mean absolute scaled error towards ARIMA, right? Some cases it does better, but in most cases it just seems to converge. This is a good thing. This is already an extremely positive result. As you see in the previous slides, right, you get significant speedups, 2 to 20 times speedups. You also get, none of the hidden costs when you're trying to scale univariate models in a cloud system that I mentioned before. So this is a very, so even with a global model that just matches the performance, the score of an ARIMA models done many singular times, is an extremely positive result for people, particularly in industry, right? A few other points to notice, like for a few low frequency data sets, so you look at the M3 yearly, Hindman also tested using sample splitting, repeated sample splitting. So essentially what they did is they fitted the global model many times across sort of segments of the global of the panel data, and then ensembled it together. And it seems to outperform the simple global model. Why this is the case? More research is probably needed. And the last thing to really notice, and this I think that the benchmarks that the Monash has done in forecastingdata.com is actually guilty of this, is that calendar and rolling features are extremely important for global models. and particularly for global models that use gradient boosted machines or random forest, so any sort of non-linear regression type model under the hood. Extremely important to have counter features, so essentially sort of time fixed effects, and also rolling features. For instance, rolling moving averages, moving standard deviation, and momentum. Extremely important, and you see this also in, say, the M5 competition, where these features are almost probably the critical features that gave 20 to 30% boost in accuracy compared to the classical models like ETS and ARIMA. Right. So what you see here, and to summarize, is with long enough memory, long enough lags, a global AR model can match the performance of, or converges towards the performance of ARIMA and many singular bases. But what I found as well from my internal benchmarks and also plenty of Kaggle competitions is once you add counter features and once you add rolling features, so or in finance they call it factors, that's where you get the massive boost in accuracy, the winning boost in accuracy, the 10-20% boost in accuracy compared to the benchmarks. So just be aware of this when you're looking at results out there that compare global machine learning models to say deep learning or benchmarks. The other type of global models, right, is deep learning as well. And right now there are two sort of, I think, probably the most high performance machine learning, deep learning models out there is something called Deep AR, which is, so I'm not an expert in this, and feel free if you do know about this, just to please jump in. Deep AR, from what I've seen, is just, my intuition is it looks like a vectorized autoregression, but just put together in a neural network. Deep AR was developed by AWS, so Amazon Web Services, for their forecasting program, and it seems to perform really well on business data sets, so things like sales and inventory management. On the right, you see this new model that was released, I think, sometime this year called NHITS. This was developed largely by the team at Nixla. They took a very different approach. So instead of using the AR structure that you see time and time again for machine learning models and also in deep AR, they looked at the literature behind, and they don't really mention this in the paper, but you can probably tease it out just looking at the graphs, literature and seasonality decomposition, and also things about Fourier transforms. So, and please, I don't know too much about it, but from what I get from it, essentially it's a form of signal decomposition. They look at all the different time series in your panel data, and they decompose it into sort of key basis functions or trends, if you want to keep it simple. And what they do is each time component of the trend, there's a coefficient that manipulates these basis functions depending on the time series at hand, and then it adds them up together to create the forecast. Seems to perform really well on data sets with strong seasonal components, which makes sense. I mean, just look at the graphs, it makes sense intuitively. So things like electricity data sets, things like weather, NHITS seems to perform, just simply outperform all current alternatives. Something to look into. I have more opinions about this as well, but perhaps you can ask me about that at Q&A. So a bit about existing Python implementations. For the AR ML global models, sktime, shout out to Dan, Leo, and Franz, are currently working on refactoring their reducer class. So it's currently supported from my knowledge, but I know there's substantial rework that's being done to sort of simplify the API. UA Darts, so this is another open source forecasting library from the Swiss consulting company Unit 8, also released an API, an implementation of autoregressive machine learning models. However, I found that it's pretty much like it's pretty much a toy model. in the sense that I've tested it with something even as little as 30 entities, and it can barely handle 2 years of data. As in the memory seems to explode, the compute times are, I have no idea when it ends. And the reason for this is essentially this. So I don't, just a quick update for people who may not be familiar with Darts. Darts has this data container called time series. And this time series data container has attributes like frequency and entities and some other things, right? But that's not the important part. The important part is actually, if you look under the hood, it's just using pandas, right? So Darts under the hood uses pandas for the shift operations. It uses pandas for their rolling means operations, and the way they compute these lags to sort of get the AR structure for the data set is an extremely iterative way, which is oftentimes required. Oh, sorry, I'm not on the same screen. One second. Let me switch my screen so you can see it. Yeah, here. So this is code from Unit 8 Darts, and you can see here that it's just using pandas under the hood, right? So this is their time series container, and they just convert it back to pandas data frame to compute the lags, and then they put it back into their time series container for follow-on operations. And what we found when I was testing Unit 8 Darts is this is the bottleneck, right? Getting the AR structure is the bottleneck. The models afterwards are fine. So linear regression afterwards, like GBM afterwards, any graded boosted machine afterwards runs as blazingly fast as it does for a simple classification regression model. But the bottleneck for time series forecasting at the moment is really this AR structure and the transformations. Is a feature engineering problem. In my opinion, the biggest thing holding back forecasting at reasonable scale is the feature engineering problem, not the modeling problem. Okay, so back to the talk. For deep learning, there are a few other alternatives. I know that sktime, there's a fantastic talk yesterday that we're working on refactoring base class. Looking forward to see where that goes in sktime. But a few more, I think, more full libraries in the deep learning side at the moment that I see is Unit 8 Darts, Neural Forecast from Nixla, and also PyTorch forecasting. In my opinion, I think the best implementations right now are in PyTorch forecasting. It's got the most wide range selection of time series models, and is also very well maintained, lots of activity, and relatively quite clean code. So if you're going to check out deep learning library for forecasting, I would definitely check out PyTorch forecasting. All right. So as I explained, at the moment, there really isn't a performant implementation of global machine learning models. And I'm proud to announce that my team is currently releasing in closed beta. So if you're interested, please contact me by email, a library called SnowMonkey. And SnowMonkey is a brand new library written purely in polars. So polars is a new data frame project in Python with a Python API, but written in Rust under the hood. And but the most important thing about polars is it's actually lazily executed. What this means is that you can actually you can run the query, you can build the query for your lags, for your AR structure, build the queries for your windowing operations all at once. The polars engine then optimizes this query so you're not sort of rerunning the windows for multiple statistics or creating the same copy of the data frame for different lags, right? It optimizes all at once so that when we create the feature engineering side for polars for global ML forecasting, it's done in an extremely fast way, and we see up to 5 to 10 speeds up in the AR structure, and in particularly around 30 to 50 times speed up for the rolling operations. But I think most importantly is the memory savings, right? Because polars is lazily executed, it can find many, it doesn't need to do a lot of redundant operations with each other. This I think is a milestone in reasonable scale forecasting, because what this means is you can now replicate some of the highest performing models in M5 competition, which was on the Walmart sales data set, on your personal laptop in minutes, according to our tests. So if you're interested in giving this a test run yourself, do email me. We're currently in private beta. We're working on the documentation, and we're also looking at potentially open sourcing it down the line. So if this is something you're interested in, do let me know. And also, if you look at a few more interesting features you might be interested in, on the right-hand side, right, we've also designed a purely functional API. So this, to my knowledge, I haven't seen this anywhere for any other machine learning library yet, where there are no side effects. What this means is that, so you can see here it's quite simple, right? You've got AR factors model. You specify your parameters. You get back your model function. There's no classes here, all functions. And then to predict, you pass in your data set, which is a lazy data set. So it's not actually loaded in the memory yet. It's just a query instruction that gets built up with follow-on query instructions under the hood of our SnowMonkey library. And the model returns a predict function. And it's only at the predict step that all the feature engineering and the computations run. And of course, we also give you the option to sort of cache your feature engineering beforehand in the model step. But if you're interested, once again, please contact me about this. So really, what's the key takeaways from this talk, right? The first one is distributed computing. So a la Hadoop and Spark, right? The paradigm which companies like Nixla, or perhaps even companies or researchers or companies like yourself right now, where you're using univariate models, were developed at global scale companies, so Google scale companies, when single instance compute and memory was a very scarce resource. Yeah, very scarce resource. But the same vertical scaling constraints do not exist anymore. And they're pretty much non-existent. I can easily go on AWS and spin up a M6i 24x large instance, which has about 240 gigabytes of RAM and I think 60 or 80 vCPUs. Right? These vertical scaling constraints that you see in the 2000s, 2010s, where they had to deal with smaller computers to run their massive scale data. And the only way to do it at that time was to build something like Hadoop and Spark, which is have many small computers and distribute your computation across many small computers. That's practically non-existent today. And in fact, it's been this case for perhaps the last 6 years. I mean, 5-6 years, right? So people in industry will probably have heard the modern data stack in the last 2 years. This revolution with companies, pushed forward by companies like Snowflake, DBT, and ClickHouse. This is testament to what I'm saying right here, which is the revival of these in-memory data warehouses and tools sort of shows that, you know, vertical scaling is possible and is perhaps more cost-effective than the distributed paradigm, right? Because with the distributed paradigm, you have all the hidden costs that I mentioned in the example beforehand. However, at the moment, in particular for in the forecasting space, we're still stuck in, well, we're still constrained by the results that seem to show that benchmark models are still extremely performant in most cases. Like ARIMA and ETS seems to perform really well in most cases. And because of the structure of that problem being an embarrassingly parallel problem, we're still requiring these distributed compute. Well, the good thing is recent research, in particular the paper that I linked beforehand from Hindman about the global models and the AR structure, it seems to suggest that global models can in fact approximate or converges towards the performance of these benchmark models with long enough memory. So the way I see it because of the virtual scaling revolution that we saw in the last 6 years, we should, in the modeling space, right? So the modern data stack is a transformation space, people doing BI, business analytics. In the modeling space, we should also be thinking about how to jump on this revolution as well, because the alternative is just stacks and stacks of layers of costs and Bezos' second trip to Mars. All right. So last thing, do we still need univariate models? Right. Yes. Benchmark models will probably never go away. Right? As I said, it's still up in the air about whether these global models can always outperform benchmark models, the singular univariate benchmark models. However, there's still significant work that has to be done, in my opinion, to make it cost effective for reasonable scale companies. First of all, we need to improve the estimation of initial values. I don't think there's enough work being done in this space, in my opinion. Right. We see extreme variance in our internal benchmarks, and also you also look at benchmarks from Hinman for models like ETS and ARIMA across different data sets. What's the reason for this? And what we found, what our hypothesis is essentially the initial values. The methods we are using to find the initial value to start before starting the optimization routine to scale the mountain or find the ideal maximum minimum is still not very well studied. And the training time is extremely variable and extremely sensitive to initial conditions. Right. And secondly, we still need a significant speed on the SARIMA. Right. Remember, I saw beforehand, SARIMA, unlike the other benchmark models, the ETS, STL, and theta, has an extremely variable, extremely variable execution time between 3 to 60 seconds. And this scales almost exponentially, depending on the number of orders that you have. So the number of AR components and the number of MA components they have. And more on this later. And lastly, we need to narrow the benchmark model space, but I don't think I have time to go into that. If you want to know what that's about, ask me in Q&A. However, there is a solution to number 2, which is, if you look at stats models, there's this open issue called Chen-Drayska's recursions, which is, at the moment, theoretically speaking, the fastest estimator for SARMA models available. Much faster than the Kalman filter, right? And we see this. These are some numbers from the paper itself that present Chen-Drayska's recursions for estimating SARMA models. You can see there's almost a 10x speed up for higher order ARIMA models estimation, right? So AS157. So AS157 is the algorithm, just the basic standard Kalman filter algorithm for estimating ARIMA models. AS197 is the recursion, the Chen-Drayska's recursion that I explained before. And you see here, right, that AS157 right now, what R uses right now and what Nixle uses in stats forecast right now, which are currently the fastest implementation of ARIMA in Python, is still extremely slow for higher orders. And we find this ourselves. So we've been benchmarking stats forecast models in our DAS cluster across around 500,000 time series. And it's still not fast enough for us. It's still not cost effective for us. But if this is implemented in stats models or perhaps directly in PM-DREAM or even directly in sktime, we could finally get ARIMA to perform at the same execution time as all the other benchmark models. And this is extremely beneficial, right? It's extremely beneficial, not just because of the speed up for ARIMA models, but it's also extremely beneficial for our for the stability of our distributed benchmarking. Why? Because extreme variability in the individual tasks that you have in your distributed compute just causes a bunch of black magic issues that can cause things to fail quite easily and the scheduler to misunderstand. But if you can get also ARIMA to work at the same speed as all our other benchmark models, this will not only make things much faster and cost effective for reasonable scale companies that still want to do univariate benchmarks, but it will also increase the stability of these systems. So, this is my email. If you want to contact me, chris@orchidbase.com. If you're interested in checking out SnowMonkey, please just send me an email, or you can find me on LinkedIn down below.